Okay, I've been giving the signal that it is time to start. So welcome everyone. Apologies for the slight delay in getting started here. And I understand that I am all that's standing between you and lunch, so I'll endeavor to keep things lively here. Hello everyone, I am Fred Rice. I work for IBM Research. And the title of my talk today is Zero-Copy Model Loading with Ray and PyTorch. And the topic of this talk is we're going to talk about why model serving is hard and why it doesn't need to be that way. So let's start with the first part of that sentence. Why is model serving hard? And when I talk about models for the purpose of this talk, I'm going to be talking about modern deep learning models. These are the very large models with many layers of linear transformations that are responsible for most of the advances in AI in the last 10 years. Deep learning models are usually deployed in production when you are serving them on top of a deep learning framework such as TensorFlow or PyTorch, and the model is packaged as two parts. There is a graph of operations that describe the transformations that go from input to output when they're applied one after the other, and there are weights that parameterize these operations. And model serving for a deep learning model consists of two major steps. First, to get the model into a place where you can use it, you need to do what is known as loading the model. This is where you first instantiate the operators of the graph, and then load the weights that parameterize these operators from disk or network, and plug them into each other to create something that you can use for the second step, which is known as model inference. For historical reasons, the first generation of AI models were literally based on first-order logic, and we're actually doing logical inference. We still use the term inference today to describe the process of running the model to go from an input to a prediction. So there's model loading, and there's model inference or prediction. And with deep learning models today, the latest generation of models have billions of parameters in their weights and require billions of floating point operations to run inference. And this makes inference in production very expensive to run, very performance intensive. However, it turns out that that first step of loading the model, just getting the model ready to run inference, is actually orders of magnitude more expensive for a deep learning model. I have a graph here over on the right-hand side of the slide that shows some timings for BERT-based. This is a commonly used natural language processing model that we use at the core of a number of our production models at IBM. And BERT-based is kind of a medium-sized deep learning model in the realm of deep learning models deployed today. Running inference with BERT-based for a natural language input about one sentence long takes 10 to 20 milliseconds if you have hardware accelerator like a GPU. It takes more like 50 to 100 milliseconds if you're running on a general purpose CPU, and that's inference. Loading the model, on the other hand, if you're loading the model from memory, that is loading it from your local computer's file system buffer cache, you're looking at about 1.5 seconds. And if you need to load that model over the network, say out of an object storage bucket, you'll be lucky to get that done in 10 seconds. So the fastest way to load this model is an order of magnitude slower than the slowest way to run inference. This means that we have to really manage this loading cost if we are going to do inference on these deep learning models in production. We need to make sure that we amortize the cost of loading over many inference requests. Now, different systems have different ways of implementing this amortization. Some systems, such as Torch serve and Ray serve, amortize this cost by maintaining a pool of long-running processes, one process for each copy of the model that you're keeping ready to run for inference. In Ray serve, that's a pool of actors, and each actor is, of course, a process. Other systems, such as TensorFlow serving and model mesh, work by having a pool of processes, but it's a smaller pool of larger processes, and they're stuffing multiple models into each process. This, of course, means that instead of having infrastructure to manage a process pool, now you have to build infrastructure to map models onto process and manage that bin mapping problem as you adjust your allocation of resources. Some other model serving systems, such as Kserve or Selden Core, put each model into a separate container. This gives you a more isolated version of that process pool model. Also gives you the option to maybe deploy a copy of TensorFlow serving in one of those containers to hybridize things. And of course, this requires all of the infrastructure for managing and routing among a pool of containers. So in all these different cases, you start out from this design problem that loading deep learning models is very expensive relative to inference. And that leads you to a place where you have this complex architecture to amortize that loading cost. And where that in turn leads you, because there are many components in this architecture, is there are many knobs to tune. You need to, as the deployer of these models, control how many copies of each model are running in each process or container. You need to manage how you adjust that allocation as the load on the system changes. You need to manage how quickly you adjust that allocation to avoid oscillations. And you have to deal with the routing of requests among these different containers if you have an application that uses more than one model at a time, and so on, right? So we have this design journey, if you will, that starts out at loading models is expensive, and it kind of ends up in a place where you have lots of boxes and arrows and lots of knobs to tune. And now there are a lot of talks in this conference that are going to talk about how you manage that complexity. In today's talk, what I would like to do is try a different direction. Try literally taking this journey in a different direction. Instead of starting out with loading models is expensive, let's try starting out in a different way. Let's try starting out by making loading models cheap. And after I've shown how that is possible, what we will hopefully see is that by using the facilities built into Ray for managing stateless tasks in parallel at scale, we can get to a point where we can get the performance of a manually tuned, very complex serving system without all the tuning and complexity part, and get to equivalent performance basically out of the box. But I'm getting a bit ahead of myself here. I think we need to start at step one. So how do we go from loading deep learning models is super expensive to loading deep learning models is cheap? Well, to get there, we need to first ask, why is it expensive to load a deep learning model? Here again, we have our timings for the BERT-based deep learning model for natural language processing. And I'm going to focus in on the third bar here, the one where it took about 1.5 seconds, to be more precise, 1.4 seconds on our test machine to load this model from the local buffer cache. And the code that we ran to do that is what we see up here. This is the standard way of loading any model in the Hugging Face Transformers library of general purpose natural language processing models. And most deep learning models have a similar way of doing loading that is, in this case, portable, in that it can handle a range of versions of PyTorch. This is a PyTorch model, a range of versions of the Transformers library that implements the graph, and a range of different versions of the model weights themselves. To get that portability, we load the model in a 3-step process. First, we instantiate the graph with some Python code, create that graph. Then we load a PyTorch state dictionary from local disk to get the weights. Then we plug those weights into the graph. And where that 1.4 seconds that encompasses these 3 steps is going is into all of the copy operations that are part of these 3 steps. Each of these steps is actually copying the weights of the model multiple times for the purpose of portability, so that we're using very narrow public APIs. And the cost of that portability is that nearly 100% of that 1.5 seconds is going to copying model weights. Now, if you're willing to give up portability across versions of PyTorch, across versions of Transformers, and versions of your weights, you can actually get much faster by pinning yourself to one version of the model and one version of all your software and serializing the model just for that application. PyTorch has a somewhat ill-documented way to do this. If you load the model with the portable way and then save it with torch.save, and then reload it with torch.load, you will hit a fast path within PyTorch that lets you load this model with one copy operation of the weights. And that gets you down to 125 milliseconds for the loading time. You can do something similar on top of Ray by serializing the model to Ray's Plasma in-memory object store and then deserializing it. This gets you down to about 1.5 copies, because when re-instantiating the model on the ray.get call, you will zero out all of the internal tensors, whereas Torch's internal implementation skips that. But in any case, if we get this down to one copy operation, that makes loading 11 times faster, which naturally leads to the question, if reducing the number of copies to 1 makes loading 11 times faster, what would happen if we reduced the number of copies to 0? Which of course leads to the question, can you reduce the number of copy operations to 0 when loading one of these giant models? Well, there are some hints that that might be possible. If you look through the documentation for Ray, there is a facility within Ray for loading NumPy arrays directly from the Plasma object store that is built into Ray without copying any of the data in the NumPy array. So if you write a NumPy array to Plasma using the code you see at the lower left here, and then read it back in, what you will get is the structure that's depicted at the right, where you have some Python objects that represent the API for accessing that array data, but the data itself resides in the Plasma shared memory segment, so no copying is done to get this array to you. So NumPy arrays can hold model weights, but they're not usable for actually doing model inference in that form, because what you need is not a NumPy array, you need a tensor, which is kind of like a similar data structure with some additional features to support the actual operations of inference. But it turns out that PyTorch has a facility for creating a tensor out of a NumPy array without copying any data. This is a little bit almost undocumented, but if you call torch.edgeTensor on a NumPy array, you will get back a tensor object for use in your PyTorch model that did not copy any of the data because it has a pointer directly to the data segment of the NumPy array. So if we chain these two operations together, we can create a procedure for loading a tensor of model weights out of Ray's Plasma object store without doing any copy operations. And so once we have that way to load a single tensor, we can, of course, power this up to loading all of the tensors that comprise the model's weights and plugging them into the model. And that gives us a three-step process for serializing a model to Plasma, so we can do loading of the model with 0 copies, and a three-step process for reloading the model. To serialize the model, first we walk through the model, identify the weights, convert them to NumPy arrays, and then replace them with placeholders. To get the model back, well, once we've written those NumPy arrays and the model graph with placeholders to Plasma, we read those back, and then we can walk the reconstituted graph again, convert the NumPy arrays to tensors without copying any data, and then plug that back into the graph, and now we have the model without doing any copy operations. So 3 steps each way. Now, of course, one of these steps in either case is a graph rewrite, and that can get a little hairy to implement. But fortunately, we have implemented that for you. We have published a small open source library, which is called zerocopy. You can get this library off of PyPy by doing a pip install, or you can get the source code. The link is at the lower left. And this library's primary functionality is to implement those 2 rewrites that enable zero-copy loading of models, PyTorch models, from Ray's Plasma object store. The one that converts the model into NumPy arrays and the skeleton of the graph, and the one that puts it back together again after loading from Plasma. So if we use the code in the zerocopy library, we can implement these 2 3-step processes with basically 2 lines of Python code. On the serialization front, this step that you do once on your application startup, first you load the model in the portable way, then you run it through zerocopy's extract tensors function. This walks through the graph that comprises the model, identifies the weights, pulls them out, replaces them with placeholders, and converts to NumPy arrays. That returns a tuple that you can directly write to Ray's object store with ray.put. And then to load the model back from Plasma without copying any of the weights data, you just call ray.get on the thing you put into Plasma, and then pass the resulting tuple through zerocopy's replace tensors function. And that gives you back a model that you can run inference on immediately, again, without copying any data. And if you load a model this way, you're loading the model and doing 0 copies. You can load BERT base in 0.0004 seconds, 4 milliseconds. So to come back to our original question, if reducing the number of copy operations for this model makes model loading 11 times faster, what happens if we reduce the number of copies to 0? Well, it gets 340 times faster. And this is a really huge improvement in the speed with which you can load any deep learning model. And this gets loading to the point where, relative to running inference on a CPU, loading doesn't really matter anymore. We can load the model every time we run inference and then throw it away. We don't have to worry about keeping that model around in between inference requests, which is going to lead to a great deal of simplicity And that's kind of the second part of the talk. Once we make it possible to load models really cheap with zero-copy model loading, how can we leverage that to build scalable model inference that reacts to changes in your application workload without having to tune a lot of parameters by leveraging Ray's built-in facilities for scheduling stateless tasks? So as some background here, here's how you would deploy a typical deep learning model to Ray without using zero-copy model loading. If you're just using Ray's facilities to maintain a pool of preloaded models, so you're amortizing the loading cost that way. Basically, you would wrap the model in a Ray actor. A Ray actor is a Python class with an associated process that is attached to the class and holds the class's state. The constructor for this actor class will load the model, which may take a second or two, but it's only doing that once. All your inference requests go to a method of the actor class, which you can invoke remotely, and that will hit that persistent copy of the model that's in memory. And to get scalability, you would create a pool of these actors and route your inference requests to the elements of the pool. We can do the same thing with zero-copy model loading with a smaller amount of simpler code. So on startup, we copy the model, we rewrite the model using our zero-copy library and load it onto Plasma. And then to do inference, we define a function like what we see on the right here. And what that function is doing is it's loading the model in a zero-copy fashion, which, as you recall, takes like 4 milliseconds for vert base. It's running inference, and then it's throwing away the copy of the model that it loaded. And that's basically it. Once you have this function, you turn that function into a stateless Ray task because there's no state that resides in between invocations of the function. And then you call ray.remote on that task, and Ray's scheduler takes care of figuring out how many copies of this function to run in parallel. And every one of these functions is only dealing with ephemeral state. So it's much simpler. You don't have to manage the size of your actor pool. And you'll notice, by the way, that the body of that function, even though we're using BERT base, that model in here, there's nothing specific to BERT base. So we include a generic version of this function in our zero-copy library, which gets that running step down to 1 line of Python code. You just call our pre-built zero-copy.call model Ray actor and pass it the appropriate parameters to run an inference on a model that's stored on Plasma without copying any weights data. Another thing to note here is memory footprint. When you are running a deep learning model the traditional way to do inference on Ray, each of those actors, if the model is BERT base, is going to need about 1,200 megabytes of standing memory in between inference requests. Whereas if we do things on the right here, we're only needing a total of 490 megabytes to store the serialized weights on Plasma. So you got 1,200 megabytes times the number of actors, which in this case there's 5 actors, so 6 gigabytes of memory required just to be locked down in between inference requests versus half a gigabyte. And the reason for this blow up is because a Python process that is ready to run inference on a model has a lot of additional overheads beyond just the packed size of the weights. Because Python's memory manager keeps extra space around to avoid reallocating buffers, and PyTorch's memory manager is also reusing buffers. And of course, there's the Python bytecode and the program execution code that you need to keep memory. All told, you're looking at a 2.5 to 3x blow up in the base memory requirement in between inference requests, multiplied by the number of copies of that model that you're keeping loaded in the traditional way, versus just keeping 1 copy on Plasma. And of course, if you put a whole lot of data onto Plasma, you also have the possibility of spilling extra data to local flash if you want to be able to enhance the amount of space you have for other uses. So to summarize here, with zero-copy model loading, we can run inference basically from a stateless Ray task, because we no longer need to keep that persistent state containing a copy of the model in memory somewhere on our cluster or in multiple places on our cluster. These weights of the model just need to be somewhere in the local Plasma shared memory segment, and we can just run a task that loads the model from Plasma and throws it away when it's done. The steady state memory footprint when we do this, even if we're keeping a copy of that weights live in your local Plasma shared memory segment, is much smaller than even 1 copy of the model kept in memory in the form of an actor. And because we don't have to manage the size of this actor pool and adjust that in response to traffic, we basically get zero tuning, but a really fast adaptation to changes in your traffic patterns, because Ray's task scheduler is going to look at the tasks it has to run and run as many of them in parallel as it needs to work through that work queue and spawn new task runners and get rid of old task runners when it doesn't need them and so on. It does all that for you behind the scenes without needing any tuning. So in principle, this gives you a way to get equivalent performance to deploying one of those really complex model serving systems and tuning it very carefully, but without the complexity and without the tuning, which of course raises the question, how well does this work in practice? Well, to answer that question, we put together a simple benchmark. And the way this benchmark works is the benchmark models a customer care chatbot application where we have an AI chatbot that's working off a pre-programmed dialog flow. The dialog flow, you can think of it as a tree-shaped graph where each node of the graph describes one state that the conversation could be in. And some of these nodes in the graph are calling out to a model serving layer that is going to do various AI tasks to derive decisions about where to move next in the graph and how to respond to the current request from the customer. And our benchmark is going to model the operation of this model serving layer that's driven by this chatbot. Inside this model serving layer, our imaginary chatbot calls on 4 different types of models. We have intent detection models to judge what is the user trying to accomplish. What is the customer, rather, trying to accomplish? We have sentiment analysis models to judge what is the mood of the user. Are they angry? Are they happy? Are they feeling okay? Do we need to switch tracks to get them onto a real human customer service rep? We have a question answering model for dealing with small factual questions that need to be answered from our documentation. And we have a natural language generation model to make the responses from the chatbot have a more natural feel and don't look as so scripted. Now, for each of these 4 tasks, because our chatbot speaks 3 different languages, we have 3 different models. Because with deep learning models for NLP, you have to fine-tune each one separately for each combination of task and language. So that gives us a total of 12 models that we need to deploy in this back end to support this AI chatbot. Now, the models that we use in our benchmark, we basically took each of these 4 tasks and went to the Hugging Face open source model marketplace and picked the most popular model in each of these categories. And then instead of actually training a copy of this model for 3 different languages, we just replicated that model 3 times to give our total of 12 models. And you can see at the chart down here some descriptions of the models. The smallest models are about the size of that BERT-based model that I talked about earlier. And in fact, are based on an enhanced version of BERT-based called Roberta. So each of these models being real natural language processing models and not just bare inference graphs have some pre- and post-processing involved in them, because deep learning models deal with numbers, and these models in application context are dealing with text. So there's pre-processing to turn text into those numbers that are the input of the model, and there's post-processing to turn the resulting numbers back into something in text form. And to shoehorn that pre- and post-processing, and also, of course, the serving part, the network I/O part, you would typically encapsulate these models inside, if you were using Ray, a Ray serve endpoint. So here's how you would run, for example, that the model that does intent detection. And deploy it to Ray serve. It's very similar to what we saw before, except I had to make the font a bit smaller because there's real pre- and post-processing code. Remember the example from earlier with an actor deploying a model? This is the same kind of thing. There is an actor class. Its constructor creates the model, but the actor is annotated with ray.serve.deployment, which tells Ray serve to create a pool of these actors and to front them with an HTTP endpoint. Inside the call method that actually uses the actor's local copy of the model to do inference, there is pre- and post-processing code, and Ray serve is going to wrap that with an HTTP endpoint. So this is how you would deploy things without zero-copy model loading, and we actually deployed our 4 models in this way to serve as a baseline. To do this with zero-copy model loading, though, all we do is we take this code for deploying on Ray serve, and we change 2 lines. Okay? In the constructor, where we're loading the model, instead of loading the model into the actor's process's local memory, we read in the model and then immediately write it out to Plasma. Now the actor process's local memory is very much, it goes back to a very small size because it doesn't have a persistent copy of the model around. The model's weights and serialized graph are now in Plasma. That's a one-line change. The other one-line change that we do is when we're running inference inside the call method of this actor, instead of running the actual inference process, doing all the math inside the actor process, we farm all that math out to a stateless Ray task that's going to load the model dynamically from Plasma, run inference, unload the model, and return the result. And so now one copy of this actor now can handle many requests in parallel because all of the actual work of model inference is running in the background in these stateless Ray tasks. And we get to that point by just changing these 2 lines of code. So once we've done that, we implemented all 4 of these models with Ray Serve. We also did a comparative implementation on top of Torch Serve, just for comparison purposes, and then we converted the Ray Serve implementations to use zero-copy model loading in the way I just described. That gives us the backend for our benchmark. The driver for our benchmark was a discrete event simulation of a number of users hitting that chatbot on the front end, and we gradually ramped up the number of simulated users. Each user would send a chat, think for a random amount of time, send another chat. And we ramped up that number of users until the response time of the backend exceeded a fixed threshold of 5 seconds because there were too many users, and then we stopped looking at the particular backend that we were experimenting with. So with this setup, the front end and the back end, and the 12 models deployed on a single parallel machine, we got these results. On the x-axis, we can see the number of simulated customers reaching our customer care chatbot. And on the y-axis, we have the fraction of requests that timed out at the machine learning layer. So obviously, you want that lower fraction is better. In fact, you want 0 timeouts. Otherwise, customers are not getting any responses. And you can see that out to about 25 simultaneous sessions, our 2 baseline deployments, Ray Serve with just 1 actor per model and Torch Serve with 1 handler per model, were able to handle things and stay underneath that designed constraint of response time. But when we get past 25, things get bad. They get bad very quickly for Torch Serve because it has more code path length, but they also get bad pretty quickly with our Ray Serve baseline because there just isn't any additional capacity to start new actors. All the memory on the machine is used by those 12 actors you have to keep around. With our zero-copy based solution, though, because all of the models are on Plasma, there's much lower steady-state usage of memory. And because everything is done in stateless Ray tasks, Ray's task scheduler can allocate all of the processing power of the entire cluster to whatever models happen to be getting the most requests right now. So this gives us end-to-end a scalability improvement where we can go out to about 225 simultaneous sessions. And that's overall a 7 times improvement in the scalability that we can achieve while still staying within our service level requirement. Now, obviously, if we took one of these baseline deployments and we carefully hand-tuned things, maybe switched to multi-threaded actors, adjusted the batching and stuff, we could probably get those baselines up pretty close to that 7x improvement. But that's kind of the whole point. We got there with zero-copy model loading by just changing 2 lines of code and tuning nothing. Because zero-copy model loading gets you 0 effort performance tuning. So thank you very much for coming to my talk. I appreciate you sticking around until lunch. We have about 1 minute for questions. If you want to find out more, our source code is available on the web, and we also have some detailed blogs. Thank you again. And we got some time for questions, and there is someone with a microphone here. I think these guys in the middle had their hands raised first. Oh, you want?
Yeah, so how does zero-copy model loading interact with GPUs?
GPUs, I have a backup slide for that. And the short answer is it's complex. So it is. We do not currently have an implementation for GPUs. There are some of my colleagues at IBM Research are looking into it right now. And other colleagues at IBM Research have done similar things in the context of model training. Basically, so there are 2 main things that are different with a GPU. First of all, to get performance out of a GPU, full performance for inference purposes, you have to do batching. It's just not an option not to. And second, the memory architecture of GPUs is complex. And I see we're running out of time, so maybe we want to take this offline if you want to go into a detailed explanation. But it's quite challenging. I would say the quickest way forward, if you want to try that, is have a setup where you copy the model to GPU memory with a single copy and amortize that copy over a batch. And you can do that on top of zero-copy model loading into CPU memory. There was a question over here.
How does that improvement go as the model gets bigger? If you scale to larger and larger models, does it hold up or does it change?
I have only done this, we've only done experiments for a small number of different models. We have a fairly narrow range of models that we're using actively in the products I work with. But generally for the larger models it works better because there is a fixed cost to loading a model in a zero-copy fashion that is about loading the nodes of the graph. And larger versions of a model tend to have roughly the same number of nodes in their graph, but much more weights data. So with a really large model, you'll get more of a speed up from zero-copy model loading than with a small model where a lot of the cost of deserializing is actually in creating those tensor objects that comprise the graph. We got one more. I'm not sure which of you was here first.
All right, thank you. From the chart that you show, after 200 chats,
Yes.
the timeout has a spike,
Yes.
even for the zero copy, right? Why,
That is correct.
why is that?
That is because we have, coming back to the chart here, the front end, the discrete event simulation, is simulating a number of users with a Poisson distributed think time in between their chats. And so what that is going to give you is a roughly a bursty distribution of the actual offered load. And the size of the burst is going to be proportional to the number of users. When that size gets too big, the number of requests that are in that burst starts to exceed what the aggregate capacity of the cluster can handle within the time limit. And everything in the burst came at roughly the same time. So basically, once you get past a threshold, you start queuing up events at the tail end of the burst every time that there is a burst. And without adding more CPU resources, there's really no way to get around that with scheduling. And the reason why you get the same kind of breakdown earlier here is because there's less free resources to allocate to whatever model happens to be getting the largest burst right now when you do not have zero-copy model loading, because you're keeping most of the cluster's resources pinned down for those preloaded copies of models, many of which are not being heavily used.
Thank
Do
you.
we have time for one more question, or do we have to send people to lunch?
Out of time, but yeah, I think we're out of time.
We're out of time? OK. I'm afraid that we're out of time, but I will be over at the IBM booth upstairs in the lounge if anybody wants to talk to me more in greater detail. And thank you very much for coming to my talk.